Okay, in this lecture I am going to discuss mean and variance of the filter. Variance. From the mean we can calculate power in the signal, and from variance we can get power in the noise. Okay, now let us discuss. See, the input is a deterministic signal and n of t is a noise. It's a random process. This is a random process. It is a deterministic signal. So as I already said, the deterministic signal plus random process, again it is going to be a random process. If the input is random process, then output also the random process. Therefore, if you have a random process, then it is characterized in terms of mean and variance. So using this mean and variance, we can define a parameter called signal to noise ratio. From the mean, we can calculate signal power or power due to signal, and from variance we can calculate the power due to noise, that is noise power. Okay, so the input to the filter is V of t, and this V of t is given by A times S of t plus N of t, and output is the convolution of your input with the impulse response. This G of t is impulse response. The impulse response operation is denoted by the star operation, and it is given by this convolution integral d tau, g of tau into v of t minus tau into d tau, and substitute this v of tau value, that is a times s of t minus tau plus n of t minus tau, and take the expectation for this one, and let us denote this expected value of output u of t is going to be a times r of t. This is just notation, okay, just notation, nothing else. So this is going to be mean. So the mean is given here, and then a times r of t equal to expected value of this whole thing will come here. Now your expectation is a linear operation, so I can exchange it with the integration operation. So therefore it is going to be integral of minus infinity plus infinity expected value of g of time tau times, let me put a here, s of t minus tau plus expected value of g of tau times n of t minus tau, the whole thing times into d tau. We can assume this g of tau, you are taking the expectation with respect to time t, not tau. Therefore this I can write expected value of, wait a minute, you can take g of tau, pull out from this expected value of n of t minus tau into d tau. Maybe 1 second, let me write it clearly, this one. So this I can say integral of g of tau times a, you can take commonly outside, expected value of s of t minus tau plus g of tau expected value of n of t minus tau minus infinity plus infinity, and we assume that the noise is zero mean noise, therefore this goes to 0 times d tau, and this is a deterministic signal. So if you take expected value for deterministic signal, then there is no change, so it will come as it is. So therefore this is integral of a times g of tau s of t minus tau times d tau. That is going to be 0, and the range from minus infinity to plus infinity. So this is your a times r of t. So this is the mean of your output process. Now look at this equation carefully. So we can mention that the expected value is essentially convolution of the input signal with the impulse response. This is the input and this is the impulse response. Therefore, the expected value is given by the convolution of input and the impulse response of the filter. Now, out of this waveform, see it is a waveform, right? This R of t is a waveform because there is a parameter time t. Okay, so out of this waveform, the value which is going to be really matter to our performance is the value at the sampling instant. So we need to sample it. See, if you look at this diagram, after this there is a sampler. So I need to sample this output. Okay, so the thing is we need to sample the waveform, sample at t is equal to t naught. Now how do we choose this value t naught? Because we don't really need to look at the mean value for all values of time. Say this is my mean, right? So this mean I cannot look at for all values of time. Okay, no need to look at all values of time. Okay, so we only need to look at the mean value at the sampling instant. Now the sampling instant is under our control. So if you assume the pulse is like this, it starts from 0 and goes to t. So you have to wait up to at least capital T, at least the pulse let it finish. Therefore, you start from 0 and wait, keep on up to this point at t equal to capital T. Therefore, the sampling instant can be chosen at least the t naught is going to be at least capital T. Therefore, your t is equal to capital T. And that means you are assuming that our pulse is sufficiently in the past. Let's somewhere less than t naught. So therefore, what you do is, this is my reference point. Let's say, let me draw here. You take a pulse like this, and let's say this is my reference point. Okay, just for assumption. So therefore, you sample at this point. Let's say here the t0 value equal to 0. It starts somewhere. The pulse starts somewhere else. Let's say minus t. It starts here. So keep on wait and it reaches 0. Okay, it's our assumption. So without any loss of generality, I will assume the following. Okay, so all this assumption is not really required, but it is slightly simplifies our analysis. That is why we are taking that t naught equal to 0 in this one. Even you can take t naught equal to some capital T also, you can do the analysis, no problem. But once you assume this t naught equal to 0, then it will simplifies our analysis. Okay, so therefore we can assume not necessarily t naught equal to 0, but I am assuming t naught equal to 0. Therefore, without loss of generality, let's say t naught equal to 0. Again, I am telling you this, not necessarily t naught will be equal to 0. It can be any value. To make this analysis simple, we are assuming this condition. Therefore, the sampling instant t naught, I am arbitrarily choosing. I am calling the instant is 0, t0 equal to 0. So that has become my reference point. So this is my reference point. Let me start from here. Let us assume that pulse started minus t. That's it. Okay. So obviously the pulse would have occurred somewhere before this t0 equal to 0. So let us assume the pulse occurred at from minus t onwards. Now, it hardly matters what is the value of t0, as long as I select it to be beyond the signal interval. Okay, so it doesn't matter where you are choosing, but the only condition is it should be beyond the signal interval or greater than the signal interval. So the only condition is should be t0 should be greater than or equal to capital T. That's it. So therefore, without loss of generality, let me choose t naught equal to 0. So if you substitute t naught equal to 0, let t equal to t naught and t naught equal to 0. Therefore, t equal to 0. So your r of t, a times r of t, if substitute t equal to 0, then it becomes a times r of 0, which is integral of a times s of t minus 0 minus tau times g of tau times d tau. So this is a times integral of, let me say, g of tau s of minus tau times d tau. This is a times r of 0. Okay. Now let us say this s of minus tau as w of tau. Let w of small w, this is w of tau equal to s of minus tau. Now do you remember the Fourier transform properties? Let me define the Fourier transform of w of tau. So w of tau, if you take Fourier transform, then you will get capital W of f, right? So now what is the relation between this W of f and s of minus tau? It is going to be W of f is equal to capital S conjugate of f. You know why this property, how it comes? How does it come? This is a general complex signal. So if you reverse the time axis, that is equivalent to conjugation in the frequency domain. Let's say s of t, if you take Fourier transform, you'll get s of f, and if you take minus s of t, you'll get either s of minus f or s conjugation of f. Okay, let us take s conjugation of f. Therefore, if you reverse the time axis, that is equivalent to conjugation the time domain. After this, t is a dummy variable. You can take s of tau also, no problem. You can put s of t, or you can say s of tau. If you take Fourier transform, you will get s of f, capital S, or you can say s of minus tau, time reversal in the time reversal in the time axis, that is going to be complex conjugate, that is going to be conjugation of the frequency axis, s conjugate of f. So that's how this relation comes. So therefore we look at the implication of this integral. This integral has implication of this integral. You will get a times r of 0 equal to a of, this is g of tau, and s of minus tau I am writing as w of tau times d tau. This a and a both sides can get cancelled, or you can keep it as it is, no problem. Now by looking at the Parseval's theorem, and before that let me square this. If you square this, a into r of 0, square this one, this is equal to square of a times integral of g of tau w of tau times d tau, square it, and this gives the power of the signal, power in the signal, because it is a contribution only due to signal component. Okay, now if you square it up and calling the output signal power, so this is the output signal power. Output signal power, just for the sake of comparison, by Parseval's theorem, this will be simply, this equation will be, let's say 1, that will be simply written as, because it is in the time domain, right? So whenever you have time domain expression for power, then the same thing you can write, you can express it in terms of frequency domain. So by Parseval's theorem, that is going to be a times integral of g of tau becomes Fourier transform, if you take g of f, and this w of tau becomes conjugate of w of f times df and square of modulus. This also your power a times r of 0 and 0. So either you can calculate power in the time domain, this is power in the time domain, and this is the power in the output power in the frequency domain. Okay, now this is the final answer which I could have easily obtained up directly and intuitively. So this answer I can get very easily by intuitive method. So let us take this is the input of the filter, this is v of t, and filter you have it, and the filter impulse is g of t. If you take for g of t Fourier transform, you will get g of f, and the output is y of t, or let's say in our response we said u of t, and if you take Fourier transform, I will get e of f. In the input domain, this is v of f, right? So how do you find the power in this case? Let's say we are assuming only noise contribution alone. Therefore, instead of v of t, let me write s of t. If you take Fourier transform, I'll get S of f. Okay, so therefore your u of t, and since this is all on noise, I can write let me rewrite the notation, it's still confusing. Let me call this is y of t, and let me call this is y of f. Okay, and this one S of f. So now in the time domain we know the expression, your y of t is equal to, the input is convolved with your impulse response g of t, but in the frequency domain this is going to be y of f equal to S of f times g of f. This is my output. Now how do you go from this y of f to y of t? By taking inverse Fourier transform. So y of t is equal to integral of your y of f times e to the j times 2 pi f t times df. So integral of your y of f is equal to capital S of f g of f e raised to 2 pi f t times df. This is your y of t. Now substitute, you are evaluating at t equal to t naught, which is equal to 0. So substitute t equal to 0 on both sides of this equation. So y of 0, which is equal to integral of S of f times g of f, and e raised to 0 times anything 0, e power 0 is 1 times df. Therefore your y of 0, this is we already wrote as a times r of 0, that is r of 0, that is S of f times g of f times df. So you can easily obtain this relation, and if you square on both sides, then y of 0 take modulus, and this is equal to integral of S of f times g of f times df, and square it. So this is your output power. So in this way also I can get it intuitively instead of going this all steps. So even without using Parseval's theorem, one can obtain the result directly. So just precisely in one line if you do the things perfectly. Okay, so that's all about how to we calculate the signal power from the filter. Therefore, when the signal is coming along with the noise, we have really at the output of the filter contributes both from the signal as well as from the noise. The contribution of the signal comes in the form of the average value of the output. Okay, because the average value of the noise we have assumed to be 0. If you look at here, the average value of the noise we assumed as 0. Where is it? Yeah, here the average value of the noise we assumed 0. Okay, so the average value of the output will be obviously correspond to the signal, which is deterministic, because signal part is deterministic. Therefore that's why I wrote here deterministic. So it will be essentially equal to this component S of t minus tau, expectation of S of t minus tau. To see the effect of noise, we have to look at the variance of the output around the average value, because we need to find out how much variance around the mean value, because that is the uncertainty associated with the output value, and that will be somehow depend on the noisy term n of t. Okay, so the n of t terms will give the noise power. So therefore now next we will look at the noise. Okay, so let me look at the noise. How do we calculate? So before that, your noise power a times r of 0 a square, this is square on the left hand side. Where is it? Yeah, this is going to be, yes, a square integral of g of tau times w of tau d tau whole square, or you can say a times, no, this is not a square, if you put square there, integral of g of f w of f df square. Okay, this you remember, this is the power in the signal. Now we like to look at what is the corresponding noise contribution in terms of noise variance. Okay, from the noise variance you can calculate the noise power, noise variance. So we will denote the noise variance by sigma square. because that will help us to write down the expression for signal to noise ratio. Why do we need the noise variance? From the noise variance we are going to find out the noise power. Already we calculated the signal power, right? So this is the signal power. Once you know the signal power and the noise power, then you can find out what is the signal to noise ratio of the filter. So it will help us to define the signal to noise ratio. So you take the square of your average mean or mean value, then that will give the signal power, and the variance will give you the noise power. Therefore, let us try to find the signal to noise ratio. In order to calculate the signal to noise ratio, then we need to find out the variance power. So the larger is the ratio, the better it will be for our detection process, for our detection purposes. So that is a point at which we will start now. So as far as noise power calculation is concerned, that one should be extremely simple, and if you do the things in the frequency domain rather than to do the same things in the time domain. So let me draw the figure again. The input is A times S of t. This is contaminated by noise. Let me write N of t here, and the output is V of t, noisy version of the signal, and this is given to the filter, and the filter response is G of t, and this is your U of t, right? V of t contains signal plus noise, and V of t is being passed through the filter G of t. So the best way to calculate noise variance at the output of any filter, you take not only this filter or any filter, whatever the filter you have it, to calculate it, the best way to calculate is simply work on in the frequency domain. So it is very good. The life will be very simple to work in the frequency domain rather than working in the time domain. Therefore, the noise contribution is the input is N of F, and how do you find out the output of a filter? See, this is your G of F, and the input is N of F. So let me write down, simplify this figure. The input is N of F, and let me call the output. The output, this N of F is the power spectral density of noise, PSD of noise. Now we need to find out the power spectral density of output. So how do you find out? The response is G of F. So generally whenever you have a filter like this, the output power spectral density is input power spectral density multiplied by square of modulus of your the impulse response in the frequency domain. So this is my output power spectral density. Okay, so the N of F is the noise power spectral density of the noise. So the input power spectrum will be multiplied by mod of G of F and whole squared. So that will give the output power spectral density. So whenever you have the power density function of noise at the output, then it's very simple to calculate the total average power in the noise. Therefore, total average power in the noise equal to area under the output power spectral density. Simple, it is very simple. So therefore, whenever you want to find a total average power in the noise, then you just take the power spectral density function of the output and do the integration over it over the range. So the most convenient way of writing down the expression to go to from is to go to the frequency domain and you can write sigma square directly. Therefore, the variance is nothing but it's a noise power. Okay, the variance tells us the total average noise power in total average power in the noise. Therefore, noise power or total average power in the noise. Power in the noise, that is given by sigma square. Therefore, sigma square equal to area under the output power spectral density function. So this is going to be area, you find it. It is output power spectral densities, just now we calculated N of F times input power spectral density times take G of F, take modulus and square of it, and then integrate from minus infinity to plus infinity. Therefore, the area under the density function will give you the output noise variance or output noise power. That is very straightforward way to calculate. Therefore, this is my sigma square. Now we have an expression in the frequency domain for output signal power. So this indicates output noise power, and here we have an expression for output signal power. So therefore we have an expression for expression in the frequency domain for output signal power at the sampling instant. This is at the sampling instant t equal to 0. And also we have an expression in the frequency domain. Look at here, this expression. Okay, in the frequency domain for the output noise variance or noise power. So therefore we have expression in the frequency domain both for signal power and noise power. So once you have these two, then you can easily find out signal to noise ratio. So therefore signal to noise ratio equal to signal power over noise power. The signal power is A times R of 0 whole divided by the noise power is sigma square. So you can substitute these two expressions. You can substitute A times integral of this is G of f times S of f df whole square divided by A integral of n of f times G of f square df. The limit is from minus infinity plus infinity. This is your signal to noise ratio of the filter, SNR of the filter. Okay, so therefore we can set up an expression for the signal to noise ratio by this expression. Okay, now in this process we have gone through how to find out the mean and how to find out the variance. What is the purpose to find mean and variance? Because the output is a noise process, it is a random process. The input is a deterministic signal A times S of t, but the deterministic signal is no longer deterministic because of the noise n of t. The noise n of t adds here. Therefore the input is a random process. Because input is a random process, then output also a random process. Whenever you have a random process like this, then you need to sample at a particular time instant. The moment you sample it, then you'll get a random variable nt, and using that for that random variable there are two parameters which are used to describe that random variable. One is mean and another one is variance. Using mean we can find out the power due to the signal. Okay, so the power due to signal can be obtained by means. The contribution of the signal is expressed in terms of power, then the contribution of the noise is expressed in terms of noise power. Okay, so we calculated the signal power and the noise power. Using these two parameters we can set up an expression for signal to noise ratio. Okay, with this expression we need to find out what is the value of G of f such that my filter will pass as much as possible signal as possible as the signal component and reject the noise as much as possible. Therefore from this expression we need to find out G of f. What could be the transfer function? What is G of f? G of f is the transfer function of the filter. Now my next job is I need to find out what could be this G of f such that my filter will pass the signal as much as possible and reject the noise as much as possible. So for that condition we need to find out the transfer function for G of f. Once you have the transfer function, then you can take inverse Fourier transform and you'll get the impulse response of the filter. From this you take inverse Fourier transform I of t, then you'll get a G of t. So this condition or this G of f is obtained using Schwarz inequality. So that we will see in the next lecture. So with this point let me stop. So we will continue from this point in the next lecture. Thank you very much.